Okay, so let's now continue. For most of the previous 1 hour, we've looked at acids and bases in terms of the Lowry-Bronsted model. I now introduce the third acid-base model, which is the so-called Lewis model. And this is very useful because just like Arrhenius had its shortcomings, so does Lowry-Bronsted. And that is because some acid-base reactions do not involve the exchange of H+. Okay? And for that we need a new model. And the model that we have there is designed by a chemist called Lewis, and we talk about Lewis acids and bases. So here, what we have here is we're not talking about acids and bases in terms of protons or OHs, we're talking about it in terms of electrons. So a Lewis acid is defined as an electron pair acceptor, and a Lewis base is an electron pair donor. Let's look at this example over here. Here we have boron trifluoride, and here we have ammonia. Now notice what's happening. We're forming something called an acid-base adduct. And what's happening is the lone pair on the ammonia is being donated into a vacant p orbital on the boron atom, and it's forming this adduct over here. This is behaving as a Lewis acid. It's picking up that electron pair from the nitrogen. It's electron pair acceptor. It's a Lewis acid. This is behaving as a Lewis base. Now, here's another example. Here we have calcium oxide, Ca2 plus O2 minus, reacting with sulfur dioxide. Here, in this case, the CaO is acting as the Lewis base because it's donating the electron pair to the sulfur, and the SO2 is acting as a Lewis acid. I should mention that this model, although I'm just briefly mentioning it today, is actually the most important of the three. This is in fact the model that you will use in further chemistry studies. This is the model you will use in organic chemistry and in inorganic chemistry. So this is extremely important, recognizing Lewis acids and bases. Okay, so here I've just categorized some examples. They tend to be, Lewis bases of course tend to be substances that have lone pairs on it. In order to figure out if there's a lone pair, you have to be able to draw the Lewis structure. You see why Lewis structures are so important. And Lewis acids tend to be electron deficient substances, or substances that can at least accommodate an electron pair. Okay. So we've basically looked at all three models: Arrhenius, Lowry-Bronsted, Lewis. And this is also, by the way, chronologically the models in historical order, right? And Lewis is the one that we use in modern chemistry. And as a matter of fact, if you're a chemist, an organic or an inorganic chemist, you almost never deal with Lowry-Bronsted, very seldomly. You work with Lewis acids and bases. This is extremely important, and you'll realize this importance in later courses. All right, well, this is just something that I guess you already know. How do you measure the pH of a solution? Well, it's very simple. You can use a pH meter, or you can use indicators. You have pH paper. You also have universal indicator, and so on, which has a certain color depending on the pH. And here, for example, you can even use cabbage juice. This is a very fun experiment we used to do in Berlin. There used to be a night of science, Lange Nacht der Wissenschaften, and we always used to do this cabbage juice experiment. So different substances react, show different, some substances that have different colors at different pH values, and cabbage juice is one of them. Now we get to, I would say, possibly the most important topic of today's lecture, and actually something finally that one would find in a first year course. And as a matter of fact, at the risk of repeating myself, when I was a student in first year university, we walked into the lecture theatre and did acids and bases. And all the stuff we've discussed for an hour, Ka and all that stuff, we didn't discuss that. The professor went straight to buffers. Okay, you see the difference? Okay. So, what is a buffer? And someone tell me, what is a buffer? It's a substance that resists pH change. Okay. How does a buffer work? Okay, now this is basically, it's something, we have buffers in nature. Blood is a buffer, for example. In other words, if there's changes in the pH, it's a system that will resist the change to that pH, because rapid pH changes are not good for biology, right? Proteins start to denature, enzymatic reactions don't take place, or they're not as effective at the wrong pH, and so on. So it's very important, particularly in biological systems, that we have a system that can resist pH changes. Now let's look at how this works. In the center here, I have basically a system. I have acetic acid, which is a weak acid, and I have its conjugate base, which is acetate. Now, that exists as a salt form. For example, sodium acetate. It's a salt. It's a salt that you have in a bottle. All right? Now, if I make a solution containing the equal concentrations of that thing over there, sodium acetate and acetic acid, what I've effectively got in solution is the acetic acid and its conjugate base. Does everyone agree? Okay. And that is a buffer. That is a buffer. And it is a buffer because it resists pH change. Look what happens if I add an OH minus. In other words, I have this is a solution, and I whack in some let's say, sodium hydroxide. What's going to happen? Well, what's going to happen is the acetic acid is going to react with that OH minus, and it's basically going to eat it up, and we're going to form more of the conjugate base, CH3COO minus, and water. This is effectively an acid-base reaction, right? Forming a salt plus water. An acid plus a base forms a salt plus water. Notice what the buffer is doing. It's basically taking care of that flood of OH minus by reacting with it. And what you end up with are two neutral products, a salt and water. But notice also that the concentration of the CH3COO minus obviously goes up a little. Now, we can play the same game if we add H+. So let's imagine we have the buffer and we add some HCl or some acid. We want to change the pH. What's going to happen there is that this acid is going to react with the conjugate base that we have in solution, or if you like, the sodium acetate. And we're going to form acetic acid plus water. Okay. So this is going to go up slightly. Okay. That is basically how a buffer works. Now, buffers have a certain capacity. In other words, you can't add, 5 milliliters of H2SO4. You can't drink 5 milliliters of H2SO4 and think that your body is going to be able to deal with that. So there's a certain capacity of a buffer, and this one can actually calculate. Okay. So buffers resist pH changes by mopping up excess hydroxide or H pluses using these two reactions here. They have a limited capacity, however, but they resist pH change. Now, to make a buffer is very simple. You need a weak acid and its conjugate base, or a weak base and its conjugate acid. In other words, you can't make a buffer with HCl. You need a weak base or a weak acid and its conjugate acid or base, respectively. Now, a very important equation is called the Henderson-Hasselbalch equation, and this comes from two guys. Henderson was an American chemist in Boston, and Hasselbalch was a Danish chemist, and they did this work around 1908. Okay, Henderson came first, and then Hasselbalch sort of refined his work a little bit. And these were the days when you could, on a Sunday afternoon, derive an equation and have it named after you, right? Very nice. Those days are gone. Okay, so let's derive the Henderson-Hasselbalch equation, which is very important in calculations involving buffers. And this derivation is also, I think, quite straightforward. So what these two guys said is, okay, let's suppose we have, let's write down a generic acid. Let's suppose it's a weak acid, HA. HA, the A is just any acid, it's a weak acid. This is obviously its dissociation equation. This is the Ka expression associated with that dissociation. Now, we can rewrite this slightly just by taking this H3O plus out of the brackets. All I've done here is I've just written that as the product of H3O plus multiplied by A minus over HA. We end up with that expression over there. No big deal. And if I now take the negative log of both sides, the negative log of both sides of this expression, I end up with this expression over here. How do I get to that expression? I get to that expression from log laws. Don't forget that the log of AB is log A plus log B. Right? That's a law of logarithms, and I use this, right, to get from here to here. So I take the negative log of both sides of the expression, and I end up with this expression over here using this log expansion over here. And basically, I rearrange this equation, and I end up with this expression over here. So negative log Ka is pKa per definition, and negative log H3O plus is pH. And basically, if I rewrite that equation, I get pH equals pKa plus log A minus over HA. And that is the Henderson-Hasselbalch equation. All right? Very simple, simply derived from the definition of a weak acid dissociating. Does everyone follow that derivation? Very simple. Very simple. You, again, sit down and do something very simple and have an equation named after you, right? Okay, so this is the equation we're going to use to calculate, to do buffer calculations. And basically, what it is that the pH of a buffer will be the pKa of the weak acid in the buffer plus the log of the concentration of the conjugate base, which will be added as some sort of a salt, sodium acetate, some sort of a sodium or lithium or potassium salt over the concentration of the acid. Okay. Now, generally speaking, for a buffer to be effective, the concentration of the conjugate base and the acid should generally be the same. Okay? And you'll see, we'll do an example of a calculation now where we see why that is the case. Okay. I mean, it doesn't have to be 1-to-1, but generally it should be within this limit over here, 0.1 to 10. But yeah, generally in a laboratory, most people make it 1-to-1, but it really depends on the situation. Okay. So let's do a simple calculation together. Oh well. Here is a calculation. All right. So what is the pH of a 50 milliliter buffer solution, which contains a 2 molar, remember that's moles per decimeter cube, which is 2 molar in CH3COOH, so that's acetic acid, and 2 molar sodium acetate. How do we proceed? Well, we plug the values into the Henderson-Hasselbalch equation, right? The concentration, so this is a classic buffer, of the acid and its conjugate base is the same. So what is the log of 2 over 2? What is the logarithm of 1? 0. The log of 1 is 0. So in fact, what is the pH? If the concentration of the acid and its conjugate base is the same, what is the pH of the buffer equal to? The Henderson-Hasselbalch equation. So I just write this as A over B, right? If that log gets taken out, what am I left with? pH equals pKa. So if the concentrations in a classic buffer system where you have a 1-to-1, doesn't have to be 1-to-1, doesn't have to be 1-to-1, it can be 1-to-10, it can be 1 to whatever, it's up to you. But if you happen to have a 1-to-1 concentration of the acid and its conjugate base, mathematically you're going to take that log out of the expression, and the pH is going to be equal to the pKa value. So very simply, here's the math. You end up with log 2 over 2. So in fact, you end up with negative log 1.8 times 10 to the minus 5, which is 4.74. So that's the pH of this buffer system. Okay, does everyone follow? All right, does everyone follow? It's simply a matter of plugging in the values into the Henderson-Hasselbalch equation. All right, next point. Now let's see how the buffer works. What is the new pH after 2 milliliters of a 6 molar HCl solution is added to this buffer? Now let's see what happens. Right, I'm now stressing the buffer system. I'm adding HCl. Let's see if the buffer does its job by minimizing the pH change. So how are we going to proceed? Well, first of all, we have to realize that we're going to have some sort of an acid-base reaction going on here, right? We have a buffer system that contains what? CH3COOH and CH3COO minus. This would be maybe some sort of a salt in exactly a 1-to-1 ratio, same concentrations. Now I'm adding HCl. What's the buffer going to do? The HCl is going to react with this guy here, and we're going to end up with sodium chloride and what? CH3COOH. Okay. So, in fact, it's going to resist the change in the pH. That's how the buffer works. So what we need to do is we need to calculate the number of moles of acid and base in the buffer. All right. Now we know that we've got a 2 molar solution, and we're adding. So the first thing we need to determine, is the number of moles of acid, HCl, that we're adding to this. Now we have the concentration, 6 molar, and we've got the volume. So we can calculate what? The number of moles, because we know concentration is number of moles over volume, right? So number of moles is concentration times volume. Remember,